Hi everyone, Hugo Bown-Anderson here. Welcome to the first full day of the SciPy conference. I'm grateful to be chairing this machine learning and data track, and I'm actually very excited to, as a first speaker today, introduce you to Leland McInnes, who's a researcher at the Tut Institute for Mathematics, otherwise known as Maths, and Computing. He's author of a number of open source tools for data analysis and machine learning, including UMAP, HDB scan, and several others. I won't list them all because they're multi-varied. Big fan, always been a big fan of Leland's work. I don't think enough people know about UMAP and these types of techniques. Among other things, I use it a lot to visualize embeddings and get a sense of what's happening with my embeddings, for what that's worth. But without further ado, put your hands together for Leland.
Thanks for the great introduction. So I'm going to be talking about how to look at your data, because that's the important thing here. Just quickly about me, I'm a researcher at the Tut Institute. My main projects are UMAP, which I spoke about at SciPy, HDB scan, which I've also spoken about at a SciPy, Pioneering Descent, which I've also spoken about at a SciPy, and DataMapPlot, which I'm going to be talking about today. So let's talk about data maps, because I think this is an important concept that's going to become more prevalent as time goes by, and I want to get people thinking about this. So a data map is just a 2D scatterplot representation of a high-dimensional data set. It's just a way of squashing a whole bunch of complex data down into something you can look at. Now, you're going to lose something when you do that squashing, but hopefully you manage to retain enough important things to show you something interesting about your data. So here's an example of a data map of MNIST digits. Each handwritten digit gets a point on this plot. You can actually see the handwritten digit displayed there exactly, and this gives you some sense of the kinds of things you can gather from this representation of your data. It is a way of looking at your data, and it can often show you useful things. But why am I talking about them? Well, it's because neural embeddings and vector databases are everywhere now. This is just a small selection of the vast array of companies that will provide you with either embeddings or vector stores of your data. We are going to end up with vast amounts of very high-dimensional vectors from all these different embedding services stored in vector stores, and we're going to need to be able to understand what on earth is in all of this. And the reality is that our visual sense is an incredibly high bandwidth channel to data. And being able to push that data through your visual sense is just going to be a much more efficient way to get insights about what's going on in that data than any other approach. Now, there's lots of different ways you can visualize your data. Data maps are a very powerful one, especially for embedding vectors. So it's just an important, powerful way to let you look at your data through a lens and see something interesting or exciting or whatever you want. Ask yourselves new questions about your data set based on what you can see. And in general, people use them either for communication as a way to show something about their data set, or for exploration to help them explore the data set themselves or help others explore that data set. So I want to give you a bunch of examples of some really nice data maps that have been presented in papers or online to give you a sense of the sorts of things that this can do when it's done well. So here's a nice example from a paper about a tool called SCPrint that was about how a transformer model could be used to separate out different gene regulatory networks, and they can present a data map of the high-dimensional vectors produced by their transformer model and show the different regulatory networks separating nicely and where the differences occur. This is a useful way to give a quick overview of how their method is managing to achieve the goals they want to achieve. Here's a different one. I really like this one because they really leaned into the old map style of view. And it's from a paper on the molecular architecture of mouse brains. But there's actually a lot of information embedded in this. If you look around the corners, there's actually little extra maps that show color maps over the base map to show you how different features interact over the structure that you see in the data map itself. Here's a nice example showing you papers from archive and bioarchive. They clustered them into major clusters here, and then, interestingly, took that clustering, and that's used to label the labels here, the colors highlighting each of those labels, from all the formulas used in those papers, where formulas are embedded to be similar if they have a structurally similar formula. And what this shows is that there's lots of different fields that use structurally similar formulas that probably never talk to each other, and maybe should. So there's great opportunities for discovery of new insights and new lines of communication out of something like this. But you can also do things interactively. So there's a great website called Open Syllabus Galaxy. You can go there and get an interactive view of millions of textbooks based on how they appear in college syllabuses. You can zoom in and so on. It's interactive. You can explore and zoom and look around and just explore the entire space of textbooks, find interesting new textbooks. A different example, there was a great paper on activations inside neural networks. This one, for the Activation Atlas paper, was on vision networks, convolutional neural networks, understanding the internal states of these neural networks and how they effectively see at different layers. Again, it's interactive. You can zoom in, pan around, explore the state space of the internals of a neural network. And if you want to understand what's going on inside neural networks, this is a very powerful way to do it. They found interesting observations about adversarial examples and so on in this paper. I highly recommend you check it out. It's well worth looking into. Another example, this was 24 million PubMed articles, all visualized in a paper by Dmitry Kobak and others, published on Nomic, and they published it as a scrolly telling. You can scroll through and learn all about what's going on, but in a fully interactive environment as well. So you actually have the full interactivity to zoom in and explore all 24 million papers. For something slightly different, on a similar vein, people have taken those techniques from Activation Atlas and applied them to large language models. So this is the internal states of Llama 3.3 70 billion. This was on a white paper by Goodfire. I, again, highly recommend this. It's a great read. They explore the different features going on inside large language models as they generate their text. And again, they present an interactive map that you can zoom in and explore through in a nice way. All right. Those were all impressive examples of data maps that communicated or allowed for exploration or just visually stunning in some way. But how do you go about generating data maps like that yourself? Because it turns out that making a good data map plot requires avoiding a lot of little traps and getting a lot of small things just right. And that can be kind of frustrating and kind of difficult. It takes a lot of work. So let's start with some of those pitfalls and look at what can go wrong. So if we talk about just static plotting, the first few examples I showed, if you want a static plot for a paper, well, it's not uncommon that you have more data points than your plot can effectively render. So if you just plot it with matplotlib with default arguments, you get something like this. And it's just a big blob and you can't really see what's going on. Of course, matplotlib is incredibly powerful and you can tweak parameters and set things up so that you can actually see what you want to see, but that takes a lot of knowledge about how to get all those things right. Fortunately, there's also a library called Datashader, which worked through all the technical details of how to do all this properly and just does it for you. So you can use Datashader and get something more like this, which actually shows you a lot more information about the structure that's going on in that plot. But it's still just a blob. You really need labels on a map like this to be able to give you information about what's going on. So how do you stick labels on? Well, if you just stick the text on, it kind of ends up not looking great. And it becomes very unreadable very quickly the more text you stick on. So what you need is some sort of complicated heuristic to manage to arrange all the labels appropriately in a way that things don't overlap and so on, or juggle them a little just so. Now, in this latter case, there's a nice library called PyLabelAdjust by Max Neuchel, which does a great job of exactly this to make the text more readable. That's something you can use, but there's still a lot of work to get all those bits working. And then we still haven't got something really attractive. If we want something attractive, we need to introduce color. And then how do I choose a color map? If I just choose an arbitrary color map based on the clusters, I can get something looking like this, which is not that great. I want to be able to pick a palette that is informative about what's going on, but also maximizes as much as possible the use of the full color space. So ideally, I want something more like this, where each cluster has its own color, but the nearby clusters have similar colors, and I've maximized, based on the data, the absolute color space used. There's a lot of heuristics to manage to make that work. You can write it yourself. It's complicated and a pain, but you can get there. So what we want to get to is something more like this, as opposed to that first plot I showed you, where this provides a lot more information easily, but it takes a lot of work to set all that up and get that to work correctly. How about if I want to do an interactive plot? Well, again, a data map can carry far more information than you can get in a single static view. Being able to zoom in and pan around and explore the data, you can find out much more information, those fine-grained clusters that are lying deep inside. You want to be able to get to and access that kind of data. But you also want to be able to get to the source data itself. You want to be able to hover over points and get information about what that point represents. You want to be able to click on a point and get further details about that point. So I want something where I can hover over points and get that information highlighted for me easily. And if I want to click on a point, I want it to take me to something with more detail about that. But I also want to be able to search and filter, to be able to explore more about the metadata attached to that plot. You can provide a lot of context with this. So in an ideal world, I should be able to text search for things and find out where on the map that text appears. I should be able to have things that I can filter by. Here, it's by time, and I can quickly swipe over and see how papers have changed over time and which fields published when. And again, while we're talking about that metadata to gain more information and context about your plot, I also want to be able to select clusters of points. I don't want to have to click on every single point or hover over a whole bunch of points to manage to figure out what's going on. I'd like to be able to select a cluster and understand what's going on in that cluster in one go. I'd also like to be able to provide that recoloring by these different metadata attributes and have that easily accessible. So I should be able to select and get information right away about the different clusters and what's going on there, and quickly get an overview of these different regions I was selecting. Or be able to pick a color map and color by something completely different, orthogonal to the plot, and see how that interacts with the nature of the plot itself. All right. Other problems, well, for interactivity, it also should scale to millions of data points. We're living with millions of embeddings at this point. We need to be able to scale to that kind of scope. And it should just work in a notebook. We all work in notebooks these days, be it Jupyter, Marimo, or otherwise, and it should ideally, as much as possible, be able to just show up in your notebook without any work on your part. But at the same time, you're producing an artifact that's useful, so you should be able to export that out to something simple, say a single HTML file that's easily shareable, so you can just send it off to somebody, or produce a bundle that you can host on a website easily. Okay, so let's put all of that together. What I want is to be able to go from the plot on the left to the plot on the right, from the basics you get from just putting things into Matplotlib with default arguments to something that captures all that detailed information, uses color well, and is aesthetically pleasing for static plots. I want to be able to go from a messy thing with a bad color palette to something that's using the color well and has those labels easily readable. The goal here is clear and effective visualizations that help tell a story, because that's really what you're trying to achieve with this. So data maps are really about asking questions. So if you're producing a static plot, you want to lead the reader to the questions you want them to ask. So here's a data map that I produced for our management at the Tut Institute, and it was just a data map of all the papers that cited Tut Institute work. And we're an institute for mathematics and computing. So the first question they asked upon seeing this is, why is cancer research and Alzheimer's and Parkinson's disease on there? And that gave us a great opportunity to talk about the value of foundational research that can apply to a whole bunch of different fields rather than just working on specific applied problems that might be of interest to them. So it led them to the questions we wanted them to ask. In an interactive case, I want to explore and find new questions to ask. Now that might be new questions that somebody else can ask, or it can be new questions you can ask. So here's an example of me searching for clustering in a map of archive papers on machine learning. And I found there was a pile on clustering, which is a topic I'm interested in, but there was another pile over nearby that was also on clustering, and there was something in between. And it turned out that the thing in between was a whole bunch of papers on optimal transport. Turns out that is a subject I should be interested in. And in fact, the paper I found and clicked on Wasserstein core sets is of great interest to me. So I found brand new papers that are really interesting easily for me. It helps me explore and ask new questions. All right, so let's talk about DataMapPlot. So the goal of DataMapPlot is to make plots like this a lot easier to build. The goal is to let you focus on the aesthetics of generating this plot, what you want it to look like, rather than the mechanics of wrangling all the things to plot. So you can produce static plots for publications. If you want to do a data map in your paper or for a poster, it should be easy to do. And it is as easy as calling create plot with the data map and labels per point of which cluster it's in, and the result is this. So you get something aesthetically great out of the box with almost no effort. And there's lots of options you can throw on to add a little more information, make it a little prettier, add some detail. If you're willing to throw in a bit of extra work, you can make it look very different and much more interesting. You can make it look like this, or like this, or like this if you're feeling whimsical and just want to communicate something a little sketchy about what's going on. What about if you want to do interactive plots? Well, that's as easy as importing create interactive plot. You just call create interactive plot with your data map coordinates, cluster labels per point, and you straight away get an interactive, explorable thing that you can zoom in and pan around. If you want to add a little more detail, ideally a bunch of different layers of clustering, because at finer grained layers of resolution there might be more interesting labels you want to apply, and the hover text, a title and a subtitle just to make it clear, you can get something that allows you to hover over points and get more information. The zoom and pan works, and now we have multiple levels of labeling that appears as you zoom in. This is all very easy to generate very, very quickly. If you want to throw in a lot more information and provide a lot more detail, you can get something as fancy as this, where we've got the ability to zoom in, we've got background images of the underlying network that's going on there, we can select points and find more information, and so on. This is all very easy to build, simple call to create interactive plot, and just specify all those aesthetic choices and add-ons that you want. Okay, so that gives you a rough idea of what DataMapPlot can do. Let's look at some actual practical examples of DataMapPlot. And I cheated because in the first examples I showed you an example that turns out was produced by DataMapPlot. The SC print paper used DataMapPlot and then used Illustrator on top of that to provide some extra plotting of the regulatory networks, but it was produced by DataMapPlot. And likewise, that Goodfire AI paper exploring the internals of Llama 3.3 was actually, their interactive example was produced with DataMapPlot internal within that paper. So let's try some live demos. maybe this will even work. The links there will take you to code that actually generates the entirety of the demos I'm about to show, from sourcing the data to building all the labels to everything. So hopefully you can track those down and try those out. So here is, if I can get my cursor over there, all of archive in a data map. And I could hover over points and find out information about them. I can zoom in as much as I want. It's all very smooth. It scales to the 2.4 million examples on archive easily. And you can find all kinds of interesting bits and pieces in here. Let me see. Down here, I think, there's a weird case where there's no papers down in that very bottom area, and then all of a sudden, there's lots of papers on it. Let's see if I can get that a little clearer. So there's a cluster with nothing, and then it suddenly fills. What's that about? Well, it turns out that's iron-based superconductors. I didn't know anything about iron-based superconductors, but it turns out they cropped up all of a sudden in around 2007, and suddenly there was a huge publishing industry for that. But what else have we got? Well, you can map the entirety of English language Wikipedia, which I've done here. I've organized it so you can zoom in on different regions easily enough. Let's zoom all the way back out and explore the entirety of Wikipedia in a way maybe you hadn't thought to explore. You can hover over points. It'll bring up a summary of the page. If you click on a point, it'll take you directly to the page, and you can read all about whatever it is you would like to read about. This is perhaps an interesting way to explore all of Wikipedia, and surprisingly easy to generate from within DataMapPlot itself. So, to wrap things up, data maps are a powerful visualization tool in the world of vector databases. But making a good data map can be challenging. DataMapPlot is a library that makes it easy to make good plots. It's easy to install. You can pip install, conda install, and it's available now. Thank you.
So much. Thank you so much, Leland, for such a wonderful talk. I'm just going to check if we have any questions yet on Slack, and I would encourage people to ask questions on Slack, and then we can read them out. Well, at the moment, as there aren't, maybe someone can put their hand up, and I'll bring the mic over to you. Just introduce yourself first as well.
Hi, I'm Jim Bavarski, U Chicago. I'm just curious if you tried this on embedding spaces to find out how large language model has tokenized words and find maybe similarities between words concepts that are in the embedding space.
So I personally haven't, but the paper by Goodfire that I linked when I was going through the slides does that for LLMs, and I think it's not so hard to do this for embedding models as well. I think there's some work by Ian Johnson on exactly this. Latent interfaces would be, I think, the keyword to search for there, where he explores embedding spaces through this sort of lens.
Do we have any other questions? What's that? Oh, really? Am I in the wrong channel? Okay. We're threading. Very good. Oh, this is a great question from Julie. What is your dream data set to use here?
So actually Wikipedia was one of my dream data sets, and I was super happy to actually be able to do that. I would love to be able to do this at scale for all of Wikipedia, multilingually, rather than just English. That's a little beyond the reach of what I can compute with right now, but maybe people would be interested in helping get things to scale up to the 60 million or so things required for all of Wikipedia.
Super cool. And if people wanted to contribute or get involved, what's the best way for them to?
Just on GitHub is the easiest way.
Fantastic. We have a question from Emily Dawn. How does the data need to be set up or pre-processed prior to calling the plotting function?
So you just need to turn the data into 2D representation. So if you want, my suggestion would be to use UMAP to do that. It will take your high-dimensional data and output a two-dimensional representation, which you can hand straight to DataMapPlot. But DataMapPlot is designed to be agnostic to this. You can use TSNE. You can use PacMap, you can use TriMap, you can use PyMDE, you can use PCA if you want. Whatever you want to get the data down to 2 dimensions so you have a 2D coordinate for each and every data point, that's all you need to do. Otherwise, it's just a matter of generating labels for clusters, and that's, again, up to you however you want to achieve that.
Great. Paul Ivanov has a question. What is the compute time like for the Wikipedia dataset, and on what kind of hardware?
The notebook that should have been linked there, it runs through pulling all the data from Wikipedia as published by Cohere, published the embeddings. So fortunately, I did not have to compute all the embeddings, but I did have to compute topic labels for all of Wikipedia using LLMs. All up, I believe that took on the order of 10 to 12 hours. I can probably get that down to something rather lower than that now. The libraries have improved, but the DataMapPlot part took about 10 minutes to chew through and output a result that you could just use. Most of the work was in generating all those topic labels, but yeah, hardware-wise, it was a large memory machine with order of 256 gig of RAM and 64 cores.
Awesome. Aaron Moira has a question. Are the colors in plots informed by the embedding algorithm, or is it a separate segmentation step?
So the colors that I'm throwing up with DataMapPlot are based on the two-dimensional representation. Because in the end, it's better to have nearby clusters have similar but slightly distinct colors than trying to manage to generate a color map that can deal with large numbers of clusters effectively. So this was the best compromise I could come up with to manage to support the wide range of use cases that we could expect for how it's done, and that's colors generated from the 2D representation.
Cool. I have a question. I'm sorry if you answered this in your talk, but so visually we can, have two-dimensional maps, but have a lot of other different dimensions within them. So what's the maximum number that we can kind of compute as humans within a visual data set?
So I figure probably, that 5 plus or minus 2 rule. So 3 to 7 is probably what you'll manage to get away with and manage to keep in your head. So, but I think the 2D representation counts as only 1 in that sense. So you can stack on for other things. I mean, there's labels, there's different color maps, there's other bits and pieces. So I think you could stack on a few extra different metadata layers.
Nice. And the most important question, can we get the slides from your talk?
I can make them available if somebody can give me a location where I can.
Yeah, absolutely. It'll be on Slack, so we'll share the slides in Slack. We had a couple of other questions that we don't have time to get to, but please do approach Leland and bug him for the next few days consistently and continually.
All right.
So, yeah.
Thank you very much.
Thank you once again.